a brief tutorial on the common ion effect and buffer solutions. Let's talk about buffers. A solution is made in which the same ion is produced by two different compounds. We call it the common ion effect because, like the title would suggest, they have an ion in common. These buffer solutions are a consequence of the common ion effect, and those are solutions that resist change in pH when acids or bases are added to them. And that buffering is because of the common ion effect, as we'll demonstrate. There are two common kinds of buffer solutions. There's solutions made from a weak acid plus a soluble ionic salt of the weak acid, like acetic acid, and then a salt of its conjugate base, sodium acetate. Or we have solutions based on a weak base, like ammonia, for example, plus a soluble ionic salt of the weak base. So if the base is ammonia, we'd have an ammonium-containing salt like ammonium chloride or something like that. So let's look and see which of these combinations could produce a buffer solution. So in A, we've got acetic acid and we got sodium acetate. So we got acetic acid and we got a salt of its conjugate base, so that's going to produce a buffer. HCl and sodium chloride. HCl is a strong acid, it's not a weak acid, so I'm not going to get any buffering there. Ammonia and sodium nitrite. Ammonia is a weak base, but the nitrite ion is not its conjugate acid, so that's not going to work. Here we have formic acid and sodium formate. So weak acid, salt of its conjugate base, that works as a buffer. So one example of this type of buffer system is a weak acid like acetic acid and a soluble ionic salt of its conjugate base, sodium acetate. So if we look at that particular example in a little bit more detail, we've got acetic acid in equilibrium with the acetate ion and a hydrogen ion. And then we got sodium acetate. It's not in equilibrium, but it will split into sodium ion and acetate ion. So there are two sources of the acetate ion. So that salt contributes a large amount of acetate ion, where the equilibrium will generate a little bit, but not a huge amount. So the weak acid will react with any base, and the anion, that conjugate base, will react with any acid. Essentially, that weak base anion will suppress the ionization due to Le Chatelier's principle to push that equilibrium back towards the reactant side, so that we don't have much ionization of the acid, and most of the acetate is due to the added acetate from the salt. So let's calculate the concentration of the hydronium ion and the pH of the solution. That is 0.15 molar in acetic acid and 0.15 molar in sodium acetate. So we're working with the same acetic acid equilibrium, except we're going to assume an initial concentration of the acetate ion, which we did not assume in our previous acid-base type equilibrias that I've done in my acid-base equilibria presentation. But the problem will work very much the same. If we start with an initial 0.15 molar acetic acid, no hydronium, and a 0.15 molar concentration of the acetate ion. Since I don't have any hydronium ion, it's going to have to shift towards products, so I'm going to lose X for the acetic acid, and I'll gain plus X and plus X on the hydronium ion and acetate ion. So my equilibrium concentrations for the acetic acid will be 0.15 minus X for the acetic acid, X for the hydronium ion, and 0.15 plus X for the acetate ion. So if Ka is going to be hydronium ion times acetate ion divided by the unionized acetic acid, we can plug in. So we get X for the hydronium times 0.15 plus X in the numerator divided by concentration of the acetic acid 0.15 minus X equals the Ka for acetic acid, which is 1.8 times 10 to the minus fifth. Now we can make our same approximation we made in the last, but even more so because the acetate suppresses that ionization. So we're going to essentially assume the plus x's and minus x's go away, because we're going to assume the x is small, so we're just going to assume it's 0 and assume 0.15x divided by 0.15 is 1.8 times 10 to the negative fifth. 0.15s are going to cancel, and you're going to get 1.8 times 10 to the negative fifth for the concentration of the hydronium ion. And then so you're going to take the negative log of 1.8 times 10 to the negative fifth and get a pH of 4.7. And you see if the concentrations are the same, the concentration of the hydronium ion will be equal to the Ka of the acid, or the Kb if you're doing one based on a base, will be equal to the POH. So if we compare the acidity of pure acetic acid solution to that of the buffer, in our acid-base presentation I did 0.15 molar acetic acid. We found in that example that the hydrogen ion concentration was 1.6 times 10 to the negative third, or a pH of 2.8. The buffer we just calculated, we found that the hydrogen ion concentration was 1.8 times 10 to the negative fifth, or a pH of 4.7. And it's about 89 times greater in the acid solution versus the buffer. Now, Henderson-Hasselbalch equation, there's a way we can work these things out a little bit more algebraically. If we've got the weak acid going to form a hydrogen ion and a generic anion, the generalized expression would be Ka is equal to H plus times A minus divided by HA. Doing some handy dandy algebra, we can work some of that out, solve it for H plus, because what we want is to calculate the pH. So H plus is equal to Ka times HA divided by A minus. I'm making the assumption that the concentration of the weak acid and the salt are reasonable, meaning that the plus X and minus X would go away, and that our approximation works. We can just say that the concentration of H plus is equal to Ka times concentration of the acid divided by the concentration of the salt, and assume that the contribution of the acid comes only from the acid and it's not really significantly ionized, and that the concentration of the salt is the total contribution of the anion, being careful of stoichiometry on the salt in particular. So if we got a weak monoprotic acid and a soluble ionic salt, the salt's cation is not univalent. You could stick an N in there to count for the concentration of the anion. You just have to be careful of the stoichiometry. With that, going back to the univalent case, we take the negative log of both sides because that'll yield a pH. Work the logarithms. You got negative log of the H plus equals negative log of Ka minus the log of the acid divided by the salt. So substituting for negative log of hydrogen ion is pH, negative log of Ka is pKa, and then distribute the negative sign into the logarithm, so plus log of salt divided by acid, so we flip numerator and denominator and got rid of that negative sign, applying our laws to the logarithms. And so that is the pH of a weak acid type buffer with a salt of its conjugate base. And that'll give you the pH of the buffer if you know the concentrations of the acid and the salt. But again, that's assuming that our approximation works and there's not significant ionization of the weak acid. The buffers can contain a weak base and a salt of that weak base. For example, ammonium plus ammonium nitrate. So we got the ammonia reacting with water to form ammonium ion and hydroxide ion. And we got ammonium nitrate dissociating to form NH4 plus and NO3 minus, where a Kb for that would be ammonium ion times hydroxide ion divided by ammonia concentration is equal to 1.8 times 10 to the negative fifth, which is the Kb for the ammonia. So let's look at an example. We calculate the concentration of the hydroxide and the pH of the solution. That is 0.15 molar in ammonia and 0.15 molar in ammonium nitrate. This will work very similarly to the previous example, except we're going to get hydroxide instead of hydronium ion or H+. So the ammonia will react with water to form the ammonium ion and hydroxide. We're going to assume that we have an initial concentration of the ammonium ion, very similar to the previous. And you can see the table looks pretty well the same. We start with 0.15 molar ammonia and 0.15 molar ammonium ion. We're going to gain X and X on that product side. We're going to lose X on the reactant side. So we're going to get 0.15 molar minus X for the ammonia, X for the hydroxide, and 0.15 plus X for the ammonium ion. So very similar. The Kb is going to work very much the same. Ammonium times hydroxide ion concentrations divided by the ammonia concentration. We're going to plug in, so that's going to be X times 0.15 plus X divided by 0.15 minus X equals 1.8 times 10 to the negative fifth. So again, since X is small, we're going to assume negligible ionization of the weak base. We can get rid of the plus x's and minus x's, and you end up in the same exact spot as you did before. 0.15 minus x divided by 0.15 equals 1.8 times 10 to the negative fifth. You could work out the algebra, but the 0.15's are going to cancel. And hydroxide ion concentration is equal to 1.8 times 10 to the negative fifth molar. But negative log of that is going to give us a POH, so negative log of 1.8 times 10 to the negative fifth is equal to 4.7. To get the pH, we'll have to subtract from 14, so pH is equal to 14 minus 4.7, or a pH of 9.3. Compare the acidity of the pure ammonia solution to that of the buffer. We've got 0.15 molar ammonia from our previous presentation of weak acids and base equilibria, 1.6 times 10 to the negative third molar for hydroxide, 11.2 for the pH. For this we had 1.8 times 10 to the negative fifth molar for the hydroxide and 9.3 for the pH. And that's about 180 times greater than in the ammonia versus the buffer. Now you can do a very similar type of derivation for the weak base. I'm not going to bore you with the mathematics, but you'll get a very similar result. For the weak base, the POH is equal to PKB plus the log of the salt divided by the weak base concentration. Now, instead of doing all that equilibria, you could just plug into these nice algebraic equations. I worked the equilibrium problem so you could see that you could calculate it that way, but you could just plug and chug into these types of formulas. So let's look at an example. Let's calculate the pH of a solution which is 0.1 molar in ammonia and 0.250 molar in ammonium chloride. In this case, we'll use the Henderson-Hasselbalch equation, and we'll use the fact that we know the Kb for ammonia is 1.8 times 10 to the negative fifth. So we need the pKb for ammonia to put it in the base version of the Henderson-Hasselbalch. So pKb is negative log of the Kb, which is negative log of 1.8 times 10 to the negative fifth, which is 4.7. Plugging that into Henderson-Hasselbalch, POH equals pKb plus the log of the ammonium ion concentration divided by the ammonia concentration, which will be 4.7 plus the log of 0.250 divided by 0.100. That'll give us a pOH of 5.1. Subtracting from 14, that'll give us a pH of that ammonia-based buffer being 8.9. So definitely in the alkaline range. So now we want to look at what happens when you add an acid or a base to a buffer, because that's the whole point of the buffer solution, as we've been talking about it, is it's a solution that's going to resist a change in the pH if we add small amounts of acid or base to it. So in this case, we're going to add 0.02 moles of gaseous HCl to a 1 liter buffer solution. That's the same buffer as we did in the previous example, 0.1 molar in aqueous ammonia, 0.250 molar in ammonium chloride. We want to look at the pH change. We're going to assume no volume change due to the addition of HCl. We're bubbling in it as a gas because we want to look at the function of the buffer and not any dilution effects. If you're doing this in the real world in the lab, you'll certainly have to include that. But for now, we'll ignore it. So what we're looking at is ammonia reacting with HCl, not in equilibrium, and it's going to form ammonium chloride. So we're going to reduce the concentration of the ammonia somewhat and increase the concentration of the ammonium ion somewhat. And those are the two ions we're plugging into Henderson-Hasselbalch. So if we look at that, we've got 0.1 molar ammonia, 0.020 molar HCl, and 0.250 molar ammonium ion. The HCl is going to react with the ammonia, and so we're going to lose 0.020 moles of each of those, but gain that much ammonium ion, so we're going to end up with 0.080 molar ammonia. We'll have consumed all the HCl, and we've got 0.270 molar ammonium ion. So running that through Henderson-Hasselbalch for the ammonia, just like we did before, pOH equals pKb plus the log of the ammonium ion divided by the ammonia concentration, or 4.7 plus the log of 0.270 divided by 0.080, which is a pOH of 5.2. So the pH is 14 minus 5.2, or 8.8. So it went down from 8.9 to 8.8, so 1/10 of a pH unit difference. Now let's look at the opposite case. Here we're going to add sodium hydroxide, or a base, to the same buffer, 0.02 moles, so same amount of sodium hydroxide. And we'll presume that we're adding a solid sodium hydroxide to the buffer, so we're not going to change the volume very much. So again, a 1 liter solution, 0.1 molar aqueous ammonia, 0.25 molar ammonium chloride. Again, let's look at the pH change, assuming no volume change. In this case, the ammonium chloride is going to react with the sodium hydroxide, and we're going to form more ammonia, and then some water and some sodium chloride. But what's of interest is that we're going to reduce the concentration of the ammonium ion just a little bit and increase the concentration of the ammonia just a little bit. So we got 0.250 ammonia, 0.02 moles of the base, and 0.1 molar ammonia. So the ammonium and the sodium hydroxide are going to lose 0.02 moles, where the ammonia is going to pick that amount up. And so we got 0.23 molar ammonium chloride, no sodium hydroxide left, and 0.120 molar ammonia. Plug into Henderson-Hasselbalch, exact same as before. pOH is pKb plus the log of the ammonium ion divided by the ammonia concentration, or 4.7 plus the log of 0.230 divided by 0.120. It's going to be a pOH of 5. Subtracting that from 14 is going to give us a pH of 9. So we traveled up a pH unit from the 8.9 pH of the original buffer. Summarizing that, you can certainly see that the original pH of the buffer we calculated was 8.9. When we added 0.020 moles of sodium hydroxide, the pH went up to 9 at a change of 1/10 of a pH unit. When we had 0.020 moles of HCl, it went down to 8.8, or a drop in 0.1 pH unit. And certainly that's significantly less than if we'd added that to an unbuffered solution, water or just a straight acid or base. But there's only a slight pH change in each case, indicating that the buffer is in fact doing its job. This has been a brief tutorial on buffers and the common ion effect.